Good morning. This is a letdown after the great keynote. We talk about elections and saving the democracy, and I was like, oh yeah, how about a little algorithm? I'll try to not disappoint too much. This talk is about is not about any language in particular. It's about an algorithm, few algorithms, in fact. And the tentative subtitle number one is that computers love boredom. In many ways, they are increasingly unlike people. They like code that's not surprising. The best code from a computer's perspective is a main function that is 600,000 lines, and it does no loops, no nothing, it just goes straight line. That would be the ideal program, which actually some of us may have written or seen in our maintenance days. Subtitle number two is, what does code that wants to be fast look like? This is a question that's been tormenting me because we don't have good intuition about, you look at code and you don't have a good intuition on things that want to be fast versus things that are not that fast at all. We do have intuition for other things. For example, this is Norway. Who drives a Tesla? Like 0 people. Okay. Oh, 1. Thank you. So I bought a Tesla, which is completely kind of a completely non-economical idea in the United States, because like everybody in the United States wants to destroy your Tesla. Like people from all walks of life. I'm not kidding. Like a nursing mother would come and scratch your Tesla with a key. Like rich people, poor people, the pizza guy, everybody wants to scratch your Tesla. They want to vandalize it. I have no idea why. And I think that they think they're doing good things, because the nursing mother, they put the baby in the car seat, and they come, they vandalize your car, and then they go to the baby. Oh, mommy did a good deed today. You know, it helps society. I don't know. So I got a Tesla, even though it's kind of a crazy idea in the States, because on geometric reasons. You see, when I was in high school, I was very passionate about physics, and I was very passionate about cars, and I was very excited to learn about the auto engine. How does it work, right? So first I go through the physics class, like the Carnot cycle, okay, fine. And then you get you see the auto engine, the internal combustion engine, the schematics and everything. And it was a bit of a letdown. I'm not sure if you even remember, there's like schematics with the cylinder and the piston, right? And it's just kind of weird. It looked like an adult toy or something. It didn't look good at all. It didn't look like it wanted to move. It looked like it wanted to produce a lot of vibration and a lot of heat. And kind of incidentally, as a perk, you could get some mechanical work out of it. And then it's like, okay, fine. So there's a cylinder with a piston. It looks like a pump or something. But you kind of transform that very awkwardly, that motion, into rotation. And okay, so that moves. Fine. So then you look at an actual motor, an engine, right? A gas engine, and it looks like a hunk of iron. It looks nothing like anything that wants to move or rotate or do anything interesting. In contrast, you have like an electric motor. It's like it wants to rotate. Just by looking at it, this thing wants to turn. It's entirely symmetrical. It makes a lot of sense. You have the stator, you have the rotor. You look at it, this thing is going to turn. So on geometrical considerations alone, I'm thinking, I want an electric motor. I don't want a motor that doesn't want to run. Instead, it wants to produce vibration and heat. Similarly, I want to figure out an answer to this question. What does code that wants to be fast look like? Anyone has ideas about what?
Short.
It's got to be short. Okay, not too long. Other ideas? Yes?
Simple.
It's got to be simple. Thank you. Other ideas?
Not very indented.
Not very indented, kind of left aligned. No, I'm not kidding. That's a great idea because so in the Unix kernel, in the Linux kernel, the coding standard is, yeah, I see someone laughing already. So indent is 8 spaces, and maximum size is 80 columns. That's your real estate. And you know, I can only assume it has to do something with efficiency, because by the time you're at a third indentation level, it's like, you know what, I don't have room anymore to do things. So you tend to avoid that. It wants to be aligned to the left. And we're going to see all of that in the code that follows. Other ideas about code that wants to be fast? Few branches that would go together with. Huh?
No, memory allocation.
Few allocations, reuse memory, yes. Other thoughts?
No raw loops.
Sorry?
No raw
No raw loops. Well, that's more for structuring. Actually, I'm against that. Like, as of 2019, all of my loops are infinite, because that's the fastest code. Infinite loops are the fastest. I realize the paradox here. There's a bit of an irony, right? Yes, Paul.
Not accessing too much data.
Not touching too much data at a time. And I think there's one more component that's interesting, which is you don't want to mix code of different heat together. You don't want to intersperse hot lines with cold lines. You want the code to have like a precise grade. Like you want your hot code to stay together, cold code stays together. The wrong thing is if I test an unlikely if somewhere in the middle of a hot loop. Okay? So let's take a look at this kind of stuff. And I'm going to use sorting both as an example, a motivating example, and as a good test bed for optimizing software. We're going to do a lot of macro optimization and quite a bit of micro optimization today. So what's the deal with sorting? It's only the most researched CS problem. Many algorithms assume, you know, let's sort that data now and see the 100 million paper on the topic written so far. So it's a very popular algorithm. And amazingly, there's still like work on sorting. People still are like, you know, drawing blood from a stone. It's amazing, right? In my opinion, every programmer must implement sort. At some point in their career, you must sit down and implement sort. All right. Anybody play an instrument? All right. What do you play?
Trombone.
Trombone. What is the classic piece that every trombonist must know? Okay. Well, what is the classic piece that any pianist must know?
La campanella.
La Campanella. Oh, that's hard. That's Brahms, Paganini. That's hard. Fiorelise. Yeah, awesome. For cellist, Bach, Anna Maria Magdalena #1. I'm not going to sing for you right now because that's going to be inappropriate. So there's a classic piece for every music, every instrument, every genre, and for you, sort is it. You must sit down and implement sort at least once in your career. And you know what? There is a likelihood you're going to implement it and make it quadratic, because I did it like several times like that. And you know, it happens. It's subtle. At any rate, Quicksort would be the algorithm of choice today in the industry. And it's the implementation standard sort in the C++ library and the implementation of even like in the C standard library, whatever. So it's fundamentally easy to code and analyze, can spend time, energy, talent on corner cases and optimization just because it's simple. It's fast on average, just like computers. It does little work on almost sorted data if you code it carefully. And this is a principle in efficient programming. Whenever you want to shuffle data, idempotent should be cheap. There is another algorithm called heap sort, right? And idempotence for heap sort is not cheap, because if you have a certain array, what does heap sort do as the first order of business? It's going to bring the smallest element to the end, the greatest element to the beginning. The largest comes to the beginning because motives, right? So that's exactly, it's going to shuffle the array so bad that actually the average case and the worst case are indistinguishable. And that's, I mean, you know, people don't use heap sort for that reason. And there's a lot of improvements to heap sort. People have worked on it exactly to eliminate this major disadvantage, which is idempotence for heap sort is not cheap. It turns out in life, very often an array you want to sort has already quite a bit of order, such as like in Python, there's team sort, right? And TeamSort looks and takes advantage of pre-sorted patterns in your data. And it's successful on a bunch of real-world cases. Now, an implementation of Quicksort would be quite simple, actually. People implement it either with a loop and one recursion or with two recursions. I want to implement it with a loop just because there's a tail recursion, which is the loop, and there's an actual recursion, which is visible here. Right? So that would be my Quicksort. So we partition, we create a pivot, we select a pivot, we partition around the pivot, and then we Quicksort the left and the right sub-ranges. Nothing sensation here. Of course, there's refinements like you detect, you use introspective sort. You kind of see if you're doing well. If you're running quadratic, then it's going to switch to a different algorithm, such as heap sort, et cetera, et cetera. But those are rare. I don't think they're germane to the essence of quick sorting. Now, what you can see if you inspect any standard library implementation and any serious sort implementation in general, you're going to see that Quicksort is poor for small data, for small ranges, right? Small amount of elements. For a small number of elements, it's not going to do that well. So what most implementations do in the real world is they're going to choose a threshold. And as long as the array to be sorted is larger than the threshold, they're going to do the quick sorting. But at the end, they're going to fall through and use a separate routine for sorting the smaller portions of the array. What happens in practice is that Quicksort is going to divide the array into unsorted, small, but properly ordered subarrays, and then there's going to be some algorithm that's going to take care of the little arrays. And this is what we're going to talk about this today. So this is the, yes?
Can we say that fast code is code that has a lot of special cases because somebody thought about it?
Fast code has a lot of special cases because somebody thought about it. Well, I think it depends here because I noticed that a lot of code with special cases is better rewritten as integrated within the general case. Actually, there's going to be an example here.
But your
Yes.
implementation wants small sort to go far too many times?
Doesn't your implementation call small sort far too many times? It does. Yeah. But it's going to be a carefully tuned algorithm for small arrays.
Here we call it.
Sorry?
It's a recursive. Okay, right, sorry. Yeah.
I think there's no unnecessary work. If that, okay. And the threshold is 1632, 16 on GCC, 32 on Visual Studio. And that's kind of a longer discussion. Maybe you should select threshold depending on the data you get here, right? Because, for example, you sort float and double. There are different sizes. So if you sort float, maybe you want a larger threshold than if you sort double, etc., because the cost of swapping those is different. But I think they want to keep it simple, so they have a set amount. Fine. So the usual implementation of small sort that you're going to find is optimistic linear insertion sort. So it starts from the left-hand side of the small array, and is going to increasingly keep the portion to the left sorted, and it's going to insert into the sorted portion the element appropriately, moving stuff around as needed. So that it's optimistic because it starts searching for the spot from the right edge, not from the left edge. Optimistic is likely to find it toward the end, right? So it works best for a little array that's already sorted. It just works perfectly. It's going to do very little work. So that would be the typical implementation. So to summarize, sorting is solved for large inputs because we just use Quicksort. Of course, there's longer discussions about corner cases, quadratic, whatever, weird data, attacks, you name it. So it's solved with qualifications and error codes and footnote, right? That kind of stuff. Small inputs is also solved from. Essentially, like optimal solutions are known for up to 15 elements. Optimal means minimum amount of comparisons, minimum of swapping, and essentially there's brute force solutions that are known to sort up to 15 elements. There's a different algorithm for each number. And this 15 has evolved over years. Like, when Knuth wrote his magnum opus, it was like, I forgot, maybe 9, 10, 12. And then people discovered it's like the latest and greatest is 15. Awesome. The problem being here, code size is going to work against that, because at 15 elements sorted, there's going to be a hunk of code that's actually going to work against you performance-wise, because the instruction cache is going to get saturated, and it's not going to become pleasant at all to use that code. So let's say, again, solve with qualifications, footnotes, and whatnot. And the most difficult problem, which I don't think is considered at all solved, is medium-sized inputs. How do you sort 1,000 numbers real fast? And this is the question we're looking at. How do you sort, not even 1,000, how do you sort 100 numbers real good? And I don't think there is a canned solution to this problem. So this is what we're going to focus on. And the challenge is essentially we want to increase threshold in this equation here in this implementation. We want to increase this as much so more responsibility is taken by a fast routine that is specialized for small arrays, small and medium arrays, and we take off the load of quicksort. Great. So that's what we're going to work on. Now, looking at std sort, the first thought, so essentially I literally took the GCC implementation of std sort, I looked at it and I said I'm going to implement something better. Believe me, it's not difficult. So it's not difficult for a specific, specific distribution, specific data, specific test, or whatever. You change a comma, you're bound to kind of just almost by happenstance to be improved by a bit. It's not difficult. Dietmar Kuhl has a talk that I think is available on YouTube. I think he called it Quicksort or something like that. And he mentions a number of improvements he made that actually beat std sort by a small margin. And it's not very difficult. And again, you should sit down and beat std sort one day, please. Okay? Homework. I'm going to only get only reds after this, right? It's like, this guy gave us homework? What's wrong with him? So if you look at the insertion sort routine, you're going to figure out that, well, here's the thing. Because I do linear search and linear insertion, I'm going to take this many comparisons, quadratic. And on average, I'm going to do half of those, which is also quadratic. So for example, for 32 inputs, I'm going to do 248 comparisons on average. Quite a few, right? Because I'm looking at like 32 pieces of data. That's quite a few comparisons. Whoa, binary insertion sort. Crack open Knuth. Binary insertion means I'm going to do binary search instead of linear search. So, oh my goodness, I'm having a much faster, much faster sort because I do much fewer comparisons, which reduce to 155 comparisons for 32 elements on average, which is a very significant decrease down from 248. Those folks are at GNU not that smart. Not that smart. So you happily sit down and code that thing. Binary search, yes, I know how to do that. It's going to take me just like 3 days, right? Because you always get it wrong, right? A few times. So anyway, sit down, you write that, you test it. Oh my goodness, this is awesome. Look at this. Test on 1 million random doubles, threshold 32. And then you instrument your code, and you get 25 million plus comparisons. And with binary insertions, you shave off 3 million comparisons. Swap stays the same, right? Because it's just comparisons that we improved. This is a 15% reduction. And the same number of move swaps, right? So very happy. So you instrument the code, you look at the code, you test the code, it all works, you assert, you have your rig, and then you time it. And it's 30% pessimization. So the amount of time you put in all that work is actually of negative literal value. So then you're like, oh, maybe I play with threshold a bit and fudge my way in. Whatever you choose for threshold, you're not going to do better than stud sort. So, and my question to you is, why did that happen? I know Paul knows. Cache.
Just jumping around.
Yeah, but okay. No, it's small data, right? So I still know you know. Yes.
There's probably some prediction involved here.
There's some prediction involved here. Indeed, what happens here is that linear searches are very predictable. With linear search, you literally fail once per search. The success rate is whatever you search minus 1. So for n, you have an average success rate of n minus 4 by n. So for 32, you're going to have an almost 90% success rate in your comparisons. Remember, computers like boring. What computers don't like is entropy, and informational entropy. Because in binary search, by definition, every comparison extracts one bit of information. It literally extracts one digit from the position. It gets from the most significant to the least significant. It extracts one literal bit of information. It's the most amount of information you can get from a comparison. And that's precisely what the computer hates. Computer's gonna, you know what? I have no idea what to do here. So there's zero prediction they can do. They're going to have an average success rate of 50%, so branch prediction is powerless. Very unpleasant. And this hints to, yes?
Well, I would assume that since it's also not very predictable, you can parallelize the search.
Since it's not very predictable, you can
It will anyway. Like
parallelize.
you can compare one in one double at a time.
I think you can, I'm sure you can code it that way. Actually, I did code it that way, and there's no improvement. I couldn't find an improvement. Okay, moving forward, it's kind of pleasant to realize that all textbooks teach you kind of the wrong thing, because they teach you that if you count comparisons and you reduce them, you're good. With sorting, it's not the case. So reality is information entropy of comparison affects performance quite radically. So what do we do? So, and it was at this point, it was a few months ago, and I said, you know, here's the thing. I'm trying all the right things, and I'm getting the wrong results. How about I try the wrong things? This is not a joke. This is like the God honest truth. And, you know, I'm basing myself on a vast experience of deluding myself, thinking that I can predict what a piece of code is going to do and how fast it's going to run. So I'm saying, you know what, optimization is surprising and complicated. You know, doing something sensible didn't work. So how about we try something completely stupid? So here's the silly idea. Show or thought. Worst case for insertion entails moving elements over large distances. So how about the silly idea? Let's make a heap in the little array, a min heap, and then we just go with a regular insertion sort. So actually, we do literally more work, because this is the previous code. I just do insertion sort, and I do more. I just do more of it. I add work, right? Okay. So you know, there's an algorithm called smooth sort, which is quite complicated. So that's not, maybe that's not very popular, but it's a bit like smooth sort, just completely stupid. And you know, what I'm hoping is that many comparisons are still predictable, so I'm not kind of ruining my predictability here. But I'm hoping that I'm going to save on swaps, because make heap is going to economically bring statistically smaller elements toward the front, right? A heap is like the minimum is the first element, and then you know, progressively the heap gets less organized, and you have like large elements and stuff like that. So fine. I wrote about this to an acquaintance who's a very accomplished mathematician and very good coder, like amazing hacker. And he wrote me a one-liner, this. And then I abandoned the idea for a couple of months. I didn't even look at it. I said, well, if he said so, it's impossible he's going to ever do anything, right? So he hated that idea, and so I hated it too. And then I had a talk to give in Italy that I had committed to, so I had no material. I had absolutely no material to talk about. So then with a gun to my head, I said, let's revisit that stupid thing. So I tested it with make heap and everything, and Quicksort does 25 plus million comparisons, almost 14 million swaps, and look at this, I reduced the number of swaps. Very interesting. I also reduced the number of comparisons, which is remarkable. So I had reasons again to get my hopes up. Didn't work. So I thought, we do too many things, and it's time to micro-optimize. And this is here's the part of social engineering that I've done. Make heap is a well-optimized routine by the authors of the standard library. It has defined characteristics. It's known. It uses the Floyd algorithm, a classic, and it's kind of a it's an optimal routine. But I thought, people who implement the standard library, that would be STL, and that would be the GNU folks, and that would be the Clang folks, and etc. People like that, they have a workload which is like, well, I call make heap once per application, per run, right? Call it once, and then I kind of manipulate them, insert, remove, that kind of stuff, right? Priority queue. But I call make heap like very few times. I wanted to call it like 100,000 times. So for that kind of workload, I assumed people would not be prepared, the implementers. So I set out to implement my own make heap. This is my speculation. So if you go to things like Rosetta code, you're going to see that heapify to heap takes a vector and is going to sift, it's going to move down elements from half of the vector and that kind of stuff. And the shift down routine is kind of, it's definitely doesn't want to go very fast because it does a lot of, it does a loop and does a lot of testing. 1, 2, 3, 4 checks of 5, 6. So it's going to do 6 tests per iteration, which is quite a few. So I sat down and did a counting here. 5 compare jump decisions, 3 add shift, 6 assignments, etc. So we must improve on that. And well, of course, let's take a look at GNU heapify because Rosetta is like for weenies. GNU is where the action goes. And let's improve this. So you gotta give them a lot of respect. Like first of all, like they need to type all of those underscores. Like it's kind of a lot of. Second, I gotta say this is very good engineering. So there's a lot of smart solutions in this. I don't have time to go over them all, but I think it's really a good piece of engineering. So what's going to happen here? We don't have a whiteboard. So what's going to happen here is a heap. It's kind of one of those implicit trees. Number 0 element is the root. Numbers 1 and 2 are the children of the root. The next layer is the 3rd, 4th, 5th, and so on. So the child of any node is 2n plus 1 and 2n plus 2, if the node is at index n, right? So this heap, the array, depending on whether it's odd number of elements. Oh, can you roll it? Oh, thank you. All right. We have a good engineer. Found a solution. Thank you very much. So as we go, thank you. All right, so I mentioned this yesterday. So we have the whiteboard, which is erasable, reusable, and we have paper to waste on top of it. All right, so here's my heap. So this is array item number 0, 1, 2, 3, 4, 5, and so on. And depending on the the number of elements in the array, the heap may end up with an orphan, not an orphan, kind of a sibling-less node, or may end with a complete, right? Okay. The problem with the GNU implementation is that it must test for this, whether I have a sibling or not. At the last element, it tests for every iteration of the loop. And that's exactly the thing. You're mixing hot and cold code together. This is exactly what you don't want to do. You want to minimize that loop. You make it as tight as possible so that you don't need to test every pass to the goddamn loop that you have a sibling or not in the last node. Ideas?
We know that's not going to happen depending on the.
Sorry?
We know that's not going to happen depending on the size of what.
Yeah, so we know a priori. The problem is, if you want, do you want to write two algorithms that are very, very different? Yes, please.
You write two loops, and you test at the very start whether you have such a sibling-less node or not.
So you write two implementations,
Yes.
but that's bigger code, right?
Test only once before you start making which.
All right. You know what? I didn't try that. But I think it's a viable thing to try. The only issue here is that the code size is doubled,
Yes.
right? But I think it's something worth trying. Thank you. Huh? What? Macros, yeah. No, it's like the generated code. Yeah. Macros, I'm not going to save that. Other thoughts? How to eliminate a cold test in a hot loop?
Put a dummy node?
Huh?
Put a dummy node? So
Put a dummy node.
like a complete.
That would work except for the last subarray. I actually thought of that. It's just like it becomes really awkward to code at the top level. Except if it's the last subarray little there. Otherwise, we can expand the net extra node. Other thoughts, ideas? All right, here's what I did. I wouldn't expect in 30 seconds anybody to find a solution because it took me like a week. Okay, so it's just gotta kind of sleep on it. So the simple solution that I implemented was I never look at this guy, whether it exists or not. I assume there's going to be an orphan node here. Not orphan, siblingless. How do you call a siblingless? Only child, yeah. A brat, okay? Apologies to those of you who okay. So we have here the node that's alone, and we ignored this node. And we build a heap. We go the heap and everything under this assumption. You can always assume there's fewer, right? But this guy remains unheapified. But then you know how to insert in a heap. You just propagate this guy up and you're done. So first you heapify everything except possibly for the last node. And as a coda, speaking of music, you're going to say, oh, let me insert the last guy into the heap. So GNU doesn't do that. Microsoft doesn't do that. But again, they didn't have a use case of, oh, I need to call this 100,000 times. Another idea that I wanted to implement here is that I want to use fewer, I want to have fewer jumps. So I talked about this, move fix up code outside the outer loop. And I didn't talk about this. We want to integrate most conditionals as arithmetic. One thing that is quite unpleasant is that comparisons are very cheap. They set a flag in the CPU, and it's like in statistically less than a cycle, you're done. The problem is if comparison is followed by a jump, because the jump is messing up with the pipeline and prediction and everything, right? So the jump is not the right thing. What you can do, however, and what is very recommendable in all situations, is to consider the return of the comparison an integer that could be 0 or 1. And if you get to integrate that integer, either 0 or 1, within your arithmetic, your normal computation, you have the condition without the jump. And it's just going to be straight line code. There's going to be no if. And you're going to reduce the number of jumps. The number of comparisons are not expensive. Jumps are. right? So we're trying to integrate conditionals as normal arithmetic. Okay? And another advantage we have here is that we take advantage of the mean heap property. The mean heap is going to be an array that has the minimum element in position 0, because by definition that's the heap. So when you insert from the right of the heap, you don't need to test for the boundary. Why? Because there's no chance to go past it because that's the smallest. You just compare. So you don't need to guard your insertion. Right? You just say, oh, as long as this guy is greater than the current element, just go left. And I'm not going to stop either here or before here because it's impossible that that anything is smaller than this guy. Right? So I have three prongs attack here. My first prong is I want to move the fixed-out code outside the hot loop. Number 2, I want to integrate conditionals as arithmetic as much as I can. Number 3, I want to do an unguarded insertion. And fourth, and this is sort of the most important aspect of micro-optimization, you must fight for every cycle like your vengeful ex. Okay? You must fight for everything like your vengeful ex. Don't, just think of like the worst date in your life, the worst fight in your life. You got to fight for every single cycle with a gun to your head. You can tell when code has been written by desperate people with their backs to the wall versus people who wanted to go home and play with the kids. Okay? You can read it. You can see the tears and the blood and the. Okay, so fight for everything in the inner loop. You must explain everything in a court of law. Okay, you must be able to defend anything to the lawyer of an insurance firm. All right. Okay, so starting with this, I'm going to say, well, first of all, I'm not going to handle even 0 size because it just so happens it's handled outside. That's, by the way, Quicksort works. So Quicksort is never going to pass me a 0 size array. So I have first and last. First is going to be less than last. I'm going to compute size, and if size is less than 3, I'm going to do a routine that sort2 is conditionally swap the 2 elements. But sort2 already integrates this as instead of an if, it integrates this guy. How does this work? What values can size have inside this if? Can be 0, 1 or 2. If size is 2, this is 1. I'm sorting to first of 0 and first of 1. So I sort 2 elements, good. If size is 1, I'm sorting first of 0 and first of 0, no up. It turns out this is faster than ifs and elses. Okay? So again, you try this, you try all this crap, every silly idea that comes to mind you try, and whatever works fastest stays. Fine. So otherwise, we have a size that's greater than or equal to 3, so we heapify, and then we do the unguarded insertion sort as promised. Why do I first plus 2 here, not first or first plus 1? Yes? The first one is already the minimum, so why plus 2? So the first is the minimum, so it should be first plus 1. First plus 2. Well,
Or the heap you've got, the first 2 children are guaranteed to be already present.
right. So this is the minimum, and this is whatever. But you can consider this as a sorted array. Ta-da! So I need to start inserting this guy into these 2 guys. Because this is less than or equal to this. And already the first 2 elements are sorted, is what I'm saying. Right? So I didn't realize this at first. 0.7%. Because instead of 1, I replace with 2. Okay? So this is already kind of, I'm telling you, it's a penny. Okay? I got a penny here. I found it. I put it in my pocket. All right. So this is the strategy. Let's implement heapify. Heapify, assert size greater than 2, remember, 3 or more. Yes. Other sizes are handled outside. And then I'm going to position myself in the middle of the array. I want to position myself somewhere half. And actually, again, I had a bug here. I wrote size -2. And again, that was a fraction of a percent. And you want to position yourself so that, in this case, size is 8. 8 minus 3, 5 by 2. 5 divided by 2? 2. So I'm positioning myself here. And this is my sort of unmanaged portion of the heap. And I'm starting here, and I'm descending nodes. And I'm creating this subheap. And then I'm going down here. I'm creating this subheap. And I'm going here, and I'm finishing the heap. If I started anywhere like here, I would do work for no good reason. So very careful with the limits. Do inner loop on the next slide. So this is where the hot code goes. This is the hot code. And then this is my fix-up code. Remember the fix-up for the last node, the possible sibling? So if size is odd, then there's nothing to do because then there's no need for that. And otherwise, I'm going to have the fix-up code. By the way, there's a clear demarcation here of hot code and cold code. And early returns are your friend. Just whenever you have an opportunity to get out of there, just get out of Dodge, okay? Just don't hang around. I've seen people actually put these in functions so that there's no cache occupied unnecessarily so people put like a function and they say, don't inline this function, compiler, please. Okay? That kind of stuff. I didn't find that necessary in this case. So fine. The fix-up code is a classic percolate up subroutine in heap. You can find it in any book. Not really nothing interesting here. It's just that I'm walking back up the heap. All right, so let's take a look at the hot loop. And as I told you, I'm a fan of infinite loops. I noticed that whenever, I interview people, I give them problems, and I say, implement this, but don't do any extra work, any unneeded work. And what students start with are fresh graduates and stuff. They start always with structured loops, and they try to kind of work their way out from there, right? And if you want to write code that doesn't do unnecessary work, very often an unstructured loop is not going to do well. A structured loop, like I equals 0, I less than n, I plus plus. That's structured loop, right? So you always should start when optimizing with unstructured loops. And then if it just turns out that it's better to structure it, you just put the structure in. But don't start with a structured loop because it warps your mind. OK, so we have the right kid is going to be dad times 2 plus 2. So starting from here, I'm going to have 2 times 2, 4 plus 2, 6. So I'm going to get here, right kid. Nice. If right kid is greater than or equal to size, we're done. And we go to the fix-up code and everything, right? Then we have the best kid would be one of these two kids, which is the smallest. And here's how we integrate math with conditions. Usually people say, if the right kid is less than the left kid, select the right kid, otherwise select the left kid. What I did here, however, is I'm taking right kid minus the comparison result, minus 0 or minus 1. A lot faster. And a colleague, Victor, said yesterday, this code looks so obvious, but it's not something that you can easily initiate, right? The inception is difficult. Once you see, it's like, yeah, whatever. So right kid minus 0, 1. So that's...
The compiler will not make those kind of things so you can write it.
No, they don't.
Have you shown it to a compiler writer?
I've discovered many instances in which compiler writers, again, they have many things on their hands to optimize, so they're not going to be able to optimize every single pattern.
You have checked? Wow.
Sorry?
Low branch there?
Oh yeah, this is a lot faster.
Yeah, but there's no branch.
Oh yeah, there's no branch. Definitely.
I just feel every time I try something similar, it always find a branch that.
Now the compiler actually can eliminate a few branches, but not most. All right. And I'd appreciate if you reach out to me in private and after this via email and show me code that produces branches, because I didn't see that. That would be interesting. Thank you. All right, so I got the best kid, which is the smallest kid. And then I'm going to compare first dad compared to first best kid to see if I want to descend this guy down the left or right side. And if that is smaller than the best kid, then there's nothing else to do in this iteration, so I'm done. Otherwise, I'm going to swap and then continue iteration. All right, so I thought for a long time how to eliminate this branch as well, and actually I found a way, but it turns out it's slower. So I just gave it up. Okay. So right now we have 3 comparisons instead of 5, but only 2 comparison jumps, and the GNU implementation ends up doing a lot more work. And in addition, we have 2 arithmetic operations and 2 assigns, and let's put this to test, see how it does. 1 million doubles, threshold 32, we're still 2% behind. But at this point, friends, I had the secret ace in my short sleeve. I had a secret ace in my sleeve, which is I can now increase threshold. I can afford a larger subarray. I can say, you know what, I'm going to take more responsibility for a small array, because right now I have this heap thing and it's going to transfer fewer elements. I have fewer swaps, so I can actually do this. So I set the threshold to double, 64, so I'm going to reduce comparisons by 2%, swaps by 1.5%, and reduces finally the runtime by 3%, which is a win. It's a measurable, significant win. Great. So that's for double. Other ties can get a lot better, actually. But wait, we're not done yet. Yes? You just ruined my moment here. Got it? Yes?
Did the result change when you try to compile with different compilers?
Different compilers. No, I just tried GCC. But it's a valid thing to worry about.
What's GCC?
9, like the latest and greatest. It was like here comes my moment. So it gets only weirder from here, friends. So we have a couple more minutes. So this is going to become like completely like right now the lights are going to go off and the universe is going to become red and that kind of stuff, right? So it's becoming weird right now. Because here's a graph comparisons. The baseline is red. This is my classic STD sort. And I'm counting the comparisons in millions depending on the threshold chosen. And as expected, the more you increase the threshold, the more comparisons you end up doing. So it's not a smart proposition to increase them too much. And I'm very happy that the blue curve is below. It means we're doing fewer comparisons with the heapify approach. So this is kind of good and expected and not weird. The same about swaps. Again, we count the swaps in millions depending on the threshold, and again, swaps grow. And I'm very happy again to see that these swaps grow a lot faster. The swaps for our implementation with heap grow, but not as bad. So, again, not a surprising result. What comes, however, is surprising, because if you time the thing, you're going to notice that as you grow the threshold and the comparisons grow and the swaps grow, i.e., you do more work, the time is going to get shorter. I swear to God, my heart is racing right now, 1:15. It's like I'm more excited than you guys. I mean, it should go the same direction. I mean, really, this is stupid. What the hell? So, okay, so at some point you kind of very nicely beat the damn thing, so very pleased with this part here. But the problem is they not both go down, and then this goes down some more, and what's going on here?
Sure I'm measuring it right?
It's you know what? I measured and went to sleep. and measure it the next day. I'm not kidding. So I rewrote the measuring code. So it was so weird that I had to make sure I'm doing the right thing. I believe I am doing the right thing. So what explanations, what hypotheses do you have here? Yes?
Again, less brushing overall because of insertion sort being more predictable?
Predictability, I'm not sure, but I'm not sure it's a factor. The problem is even for a given algorithm, for example, for this heapify based approach, the time goes down even though swaps go up, comparisons go up, so quite literally you do more work by all metrics, swaps, there's more moving memory, there's more comparisons, and yet the time goes down. It goes down like up to here. There's a lot of data points here. Other thoughts? Yes?
I mean, you're doing fewer partitions now, so you're doing more work.
There's fewer partitions.
Because the threshold's larger, right?
Right.
So it could arise from, I mean, it's obviously your inner thing.
Okay.
Than
I do count the comparisons and the swaps in partition as well.
yes.
So I count everything. So there's nothing I'm not counting is what I'm saying, right?
Yeah.
So I think what I'm saying is the counts are useless. Yes?
Maybe your tiny or short sort has better locality when addressing the elements as opposed to quick sort.
Thank you. So maybe there's some better locality because heapifying the thing is going to avoid moving elements over large distances. It's going to kind of move them carefully to the front. So that's my hypothesis as well. Thank you very much. Sweet power of 2, just to summarize, for double is 256. So we improve on STD sort by 6%, which is significant and very pleasing. By the way, sorting, you should know, is not a high margin business. You can't do the 3 times the speed of std sort. There's a limit. Like Knuth proved a limit, a theoretical limit, which is n log n times a constant minus n times another constant. And you can't get a lot better, right? So 6% I'm very happy with consistently, right? So that's great. And here's the metric I'm working on right now. I'm collecting the average distance between 2 subsequent array accesses, right? So if I read or write an array element and I read or write another array element, I take the distance between them and I postulate, just because I can, just because nothing else is useful, I postulate that the smaller the distance, the better the algorithm. If I mess with elements that are very far apart, then not a good algorithm. If I mess with things that are close together, better algorithm. So I hope that this is going to be a good proxy for locality of array accesses. With Quicksort, d of n is large. For insertion, heap insertion, d of n is smaller, which explains our results. And d of n decreases with threshold, again explains our results. And my contention here is that comparisons and swap don't tell the whole story. And indeed, average access distance does go down with threshold. And even more so, with classic insertion sort, it goes down faster. Why? Because insertion sort just looks at the next element. It's just the most economical in that, but it does a lot of comparisons and swaps. So you got to look at all of the above: comparisons, swaps, and distance. Okay, you can't look just one metric and conclude, right? Wow. Okay, interesting. To summarize, I'm noticing with increasing frequency and worry that books that are considered like sacred cows are no longer that sacred. Because every book you crack on algorithm is going to tell you if you improve on comparisons and swaps, you're improving on the performance of sorting, which is simply not the case. So there's a divergence between established theory and practice. So I would suggest you try silly things and measure, because silly things plus good measurement equals surprising results. So to improve your intuition, devise and track meaningful metrics such as this proposed distance. You've been great. Thank you very much. Thank you.